Welcome to our exploration of gamified fabrication learning. We'll look at how game thinking and hands-on making come together to transform education, what the latest research says, and where the field is heading. Think of it as bridging playful engagement with the real-world impact of building things, from classrooms to makerspaces, with a pragmatic lens on outcomes, equity, and implementation. Here's the big picture. Gamified fabrication blends game design with physical making to amplify motivation and skill growth. It's well known in general education, but less examined in fabrication itself. The slide highlights rising hybrid digital physical platforms, interactive challenges, and meaningful feedback, alongside hurdles like scalability and aligning fun with learning goals. Our aim is to guide educators and designers toward evidence-based, interdisciplinary practice. To motivate, make, and master, we combine game mechanics like challenges and rewards with hands-on fabrication using tools such as 3D printers and microcontrollers. A hybrid approach in maker environments channels creativity while reinforcing practical skills. This model sits comfortably within constructivist and experiential learning theory, where learners progress by doing, reflecting, and iterating with clear goals and supportive feedback. Why a new angle is needed? Most studies isolate gamification from fabrication, leaving few frameworks for playfully structuring making activities. Effective systems must balance curricular objectives, learner enjoyment, and material constraints like tools, time, and safety. The gap calls for interdisciplinary research that links human-computer interaction, learning sciences, and design to ensure rigor and real-world applicability. Our objectives are straightforward. We synthesize prior work on gamified fabrication to surface trends and unresolved questions. We analyze how specific game mechanics interact with fabrication workflows. And we translate those insights into practical guidance that helps educators, researchers, and designers craft engaging maker experiences while also sharpening the theoretical foundations that support them. This review follows a Prisma-style protocol to ensure clarity and replicability. We searched 7 major education and engineering databases, including IEE Explore, the ACM Digital Library, Scopus, and Google Scholar. We focused on empirical studies, excluding theoretical pieces and non-English works. Search terms balanced precision and breadth to capture gamification within fabrication education without drifting into unrelated domains. We analyze the field through 3 complementary lenses. Gamification in education explains how points, challenges, and rankings can heighten engagement. Fabrication in education centers on hands-on making with physical and digital tools. Online petition design examines collaborative platforms that coordinate participation and feedback. Together, these perspectives reveal how learners co-create, iterate, and stay motivated in hybrid learning ecosystems. The selection diagram shows a rigorous filtering process. We identified 377 records, removed duplicates, screened out non-educational or opinion pieces, and assessed full texts against empirical criteria. In the end, 11 studies met the bar. This careful funnel ensures our conclusions rest on measurable outcomes and methods rather than anecdote, providing a sturdy foundation for guidance. Across 2016 to 2025, the trend is intermittent but rising. Early activity around 2016 gave way to a first publication peak near 2019, a lull and renewed momentum in 2024-2025. The overall pattern aligns with the growth of edtech and makerspaces, suggesting that infrastructure, access, and teacher readiness are key drivers of research and classroom uptake. The publication pattern is recent and concentrated, with gamification serving as the central theoretical anchor. Growth appears bursty, where periods of intense activity are followed by consolidation and reflection. The image of notes and markers nicely captures this iterative planning energy. Overall, the field is young, energetic, and increasingly aligned with broader educational technology trends. Let's compare approaches often used in computer science education. Gamified teaching tools scaffold complex topics with stepwise challenges and rewards. Game-based activities in workshops and labs boost motivation and achievement in programming fundamentals. Digital self-paced platforms emphasize mastery of abstract concepts and cognitive engagement. Together, the examples show how design choices shape motivation, persistence, and conceptual depth. Here we shift from screens to tools in hand. Studies applied gamification to physical assembly and fabrication, sometimes powered by machine learning that provides real-time feedback. Outcomes improved for both learning and design quality, echoing strategies familiar in computer science. like progress tracking and rewards, yet grounded in tangible artifacts. The takeaway is clear: align challenges to real making goals, then close the loop with data. Now we connect education levels. In K-12, digital fabrication turns abstract ideas into tangible outcomes, building problem solving and teamwork. In secondary school, rapid prototyping strengthens STEM integration and design iteration. In informal makerspaces, open-ended exploration advances hands-on mastery and creative confidence. Across contexts, fabrication pushes thinking from hands-on to head-on, linking creativity with engineering rigor. These panels illustrate K-12 applications. 3D printing enables iterative prototypes that teach design thinking and spatial reasoning. Laser cutting supports precise testing and material literacy. CNC and vinyl cutting reinforce repeatable production and measurement. Electronics and microcontrollers connect STEM concepts to real functionality. Studies report gains in creativity, critical thinking, and practical skills, making abstract ideas concrete in the classroom. In higher education, digital fabrication anchors prototype-driven learning and cross-disciplinary collaboration. Rapid prototyping builds iterative design habits essential to professional engineering. Shared projects connect students from multiple fields, strengthening communication and systems thinking. As the images suggest, the studio and lab become a common ground where theory meets practice, and learning outcomes include competence, iteration, and teamwork. Informal makerspaces bring different strengths. Shared tools nurture community and peer collaboration. Open access invites self-directed exploration beyond formal curricula. Diverse backgrounds come together, stimulating motivation and creativity through projects and experiments. These spaces also support social inclusion and lifelong learning, fostering confidence and independent inquiry that can later transfer back into classrooms and careers. To coordinate collaborative making online, we map platform features to pedagogy. Decision and participation tools, like voting, roles, and quorum rules, support collective choice and leadership. Reflection and critique thrive through threaded feedback, version history, and moderation. Progress and momentum are sustained by dashboards, badges, and timely reminders. The classroom photo underscores how digital scaffolds can amplify real-world projects. The evidence is compelling. Allowing learners to vote on projects increases engagement compared with instructor-assigned work, while peer feedback and iterative prototyping raise completion rates. When combined, these mechanisms also improve design quality and model authentic collaborative workflows. In short, democratic choice plus structured feedback fosters social learning, better decision-making, and stronger outcomes from concept to completion. Progress tracking keeps communities moving. Visualizing contributions and milestones boosts motivation, and leaderboards can highlight effort when designed with care. Studies report a substantial reduction in project abandonment during longer tasks, while also noting challenges of scalability and fairness. Designers should integrate social learning and collective intelligence, then test for equitable involvement as participation grows. Several insights emerge. Points, badges, and leaderboards consistently elevate engagement and skill development in fabrication contexts. Yet narrative framing and rich feedback remain underused despite their power to deepen learning. Findings align with constructivist theories that value physical interaction and reflection. A key tension persists between prescriptive mechanics and creative autonomy, an invitation for studies that support learner agency. For practice, blend online coordination with offline making so collaboration mirrors authentic fabrication. Define accessibility requirements early to avoid excluding learners. Use gamification purposefully, aligning mechanics to objectives rather than surface-level fun. Interpret results cautiously given publication bias and language limits, and keep updating reviews as new studies emerge. The goal is balanced innovation grounded in evidence. Looking forward, we need longitudinal research on retention and long-term impact, comparisons of methods across diverse learners, especially underrepresented groups, and adaptive systems that personalize challenges to progress. We should study social collaboration that encourages inclusion while probing AR and AI as emerging supports for gamified fabrication. Across all directions, prioritize equitable access alongside innovation and rigor. Bringing it together, gamified fabrication couples the engagement of games with the real-world value of making. Evidence shows strong learning and skill transfer benefits, but adoption can be limited by complexity and access. Our call to action is inclusive design, rigorous evaluation, and cross-disciplinary collaboration. The outlook is promising if we integrate theory, pedagogy, and pragmatic implementation at scale. Here are the core takeaways. Gamification boosts participation and fabrication skills when woven into hands-on tasks. Learning potential is held back when narrative and feedback are inconsistent. Aligning game design with fabrication's cooperative, practical nature yields meaningful gains, while superficial mechanics alone fall short. Deep integration of storytelling, feedback, and collaborative practice is the path to lasting impact. To realize the future, connect gamification tightly with maker pedagogy, guiding tool and curriculum development for game-based fabrication. Prioritize accessibility and scalability when deploying solutions. Advance research on longitudinal assessment and adaptive systems, and explore social collaboration and emerging technologies to widen effect. Ultimately, pursue evidence-based, inclusive innovation so more learners can make, iterate, and thrive.